Okay, so welcome to this session of the lecture. So today we will discuss more about rotational spectroscopy. So in the last lecture we saw that the degeneracy of any rotational energy level depends on the orientation of angular momentum vector, correct? And that degeneracy was given by mj, this mj term. And this mj is defined as 2j plus 1, meaning any rotational energy level is 2j plus 1 fold degenerate. So when we apply the electric field, further when we apply any electric field, so what this electric field will do, it will lift off this degeneracy. What is the meaning of this lift up? So let's try to understand that with the help of one example. For j equal to 2 level, we will have 5-fold degeneracy. So 2 is 2 plus 1, 5-fold degeneracy. So when we do not apply any electric field, in that case, I am saying this field off, means no electric field here, okay? No electric field. So in this case, all the 5 levels will be degenerate, meaning all these 5 levels will have same energy. Okay. But when we apply the electric field, in that case, what we are seeing, the energy of plus minus 1 level or 0 level is getting lifted, while the energy of plus minus 2 is decreased. Then what? Then the initial energy value. Okay. So in this case, and in this case, energy of different level is getting lifted, and this effect we call Stark effect. So when the Stark effect comes into the picture, then we will have additional selection rule. That is delta mj is equal to 0 or plus minus 1. Okay. And the energy of any rotational level after the application of electric field is given by this equation. Okay. So this first term, if you are seeing, this term is nothing but without any electric field. Excuse me. This is without any electric field. Any electric field. And this term is coming because of interaction between the dipole moment of the molecule and electric field. So when we are applying the electric field, so what is happening? This electric field is interacting with dipole moment of the molecule. So this is interaction term. So this mu is nothing but dipole moment, and this is electric field. Okay, this is due to electric field. So then why we are interested in studying this? Okay, we are interested because in this, by applying electric field, we can calculate the dipole moment of any unknown molecule. Okay, we can calculate this mu. Let's say we discovered some molecule, we don't know anything, then we can record our rotational spectrum, and then we can calculate this mu. Okay. Further, so these are the summaries of lecture 17. Okay. And further, we saw in the last lecture also the intensity of rotational line. Okay. So we saw like some rotational structure of carbon monoxide. We saw like this. Something like this. This is intensity, and this is your centimeter wave number. Okay. So we can see here that the intensity of this peak is higher than others. Why is it so? So we try to see there how the intensity depends. So this intensity will depend on, let's say this rotational line is coming from 0 to 1 transition, and this is coming from 1 to 2 transition, like j equal to 1 to j equal to 2, and this is coming from 2 to 3, and so on. So intensity of this line is higher. What does it mean? It means the transition between j equal to 2 to j equal to 3 is maximum. And when this transition becomes maximum, when the population, that is number of molecules in j equal to 2 will be maximum. Okay. In that case only, the transition from j equal to 2 to j equal to 3 will be maximum. So let's try to understand that. How can we evaluate it? How can we predict the intensity of rotational spectrum or rotational lines? To see that, we took two energy level, j equal to 0 or j equal to j. Okay, this is j in rotational energy level. Okay, so this population, this ratio population, or we can say relative population, let's say transition happening from j equal to 0 to j equal to j. Okay. So the relative population here corresponding to here is given by Maxwell-Boltzmann distribution. This is Maxwell-Boltzmann distribution. Okay, and we derived in detail in the lecture note also, in the previous session also. And this is given by 2j plus 1 e to the power minus bhc j into j plus 1 by kt. This is thermal energy. Kt is nothing but thermal energy. And when we solve this, so what we are doing, we are solving for maximum j. What does it mean? We are solving for a rotational energy level that has maximum population. So how can we solve that? We solved like this. For maximum, we did derivation with respect to j, and we found j max like this. Okay, using this condition for maximum. Okay, and when we substitute this value k, h, c, we got some kind of this value. Okay. So we can see here this j max depends on two things. One is temperature of the system under the consideration, and the second is this rotational constant. Okay, so this is the calculated j max, but let's try to understand the distribution of the molecule in different rotational energy level using this Maxwell-Boltzmann distribution. So if you see this equation, this population depends on two terms. Depends on two terms. I will highlight that. So first is this term, and the second I will write 1, and the second is this term. I will write 2. Okay. So if we ignore the second term, then this become linear function, correct? See, we'll get something like this with slope, with intercept of 1. Okay. And if we ignore the second term, then it's exponential decaying function like this. Okay. But when we'll combine both term 1 and term 2, so what will happen? Initially this term 1 will dominate. Okay, so we will get something like, sorry, so initially the term 1 will dominate, then after some time, after some jth level, this exponential term will dominate. Okay. So you'll have something like this kind of distribution. Okay, till here this first term dominated, and after this point, the second term dominated. So we are interested in getting this point, getting this j. That will be our j max. So these are the summary of lecture 17, where we understood the how this intensity of rotational lines depend or get affected, and what is the effect of electric field we saw here. So based on this summary, let's try to solve some problems. Okay. So the first question, which option is true for intensity of rotational lines? So we have to understand what is rotational line first. So let's say this is an energy level diagram. So this is different rotational energy levels. Okay. So I am saying 0, 1, 2, 3. This is jth level. Okay. So some transitions happening from g equal to 0 to 1, and then 1 to 2, and then 2 to 3. And because of this transition, we are getting some rotational spectrum. So we are plotting intensity against wave number. Okay. So we are getting some kind of one spectrum because of 0 to 1, 0 to 1, and then another 1 to 2, and then another 2 to 3. We will not get this kind of line, we will get some broader spectrum, and the reason for broadness we have already explained in lecture 2. Okay. So I am, for sake of convenience, I am writing straight line, but we will not get a straight line in actual scenario. Anyway, this line, this line in the rotational spectra are called rotational lines. Rotational line. Okay. So the question is asking on what factor this intensity will depend on. Okay. So the first is depends on the population of initial state and transition probability. Second, initial state and not in transition probability. Independent of population. That is wrong. That is wrong. So let's try to understand that. Okay. So if we have a higher number of molecule here, that is higher number of population, then we will have higher number of transition. Okay. In that case, we will have higher intensity. So definitely it will depend on population. Now, whether it will depend on transition probability or not. So transition probability, let's say we are giving some 2 energy level here. I will say 1, 2, and then transition probability we can write like this. That is probability dependent on a square of transition dipole moment integral. So we can write psi 2 star mu psi 1 d tau. So this integral will be higher only when we will have like this integral probability density or transition probability will increase with increasing in population. So first option will be the correct choice. It will depend on population of the initial state as well as transition probability. Okay. Now coming to the next question. Okay. The ratio between population of ground state and other excited states at lower j value, at lower values of j, mostly depends on. So I wrote this equation, correct? This n, sorry, so we wrote this expression n initial or n0, we got something 2j plus 1 e to the power When I am writing directly delta E, okay, instead of expression for delta E by KT. Okay, so we plot like this kind of expression, this kind of distribution, and we saw that initially this term 1 dominates, and after some time this term 2 dominates. Okay, so what this question is asking, at lower value of J, this ratio will depend on this term. Okay, this will dominate. Now coming to the next question. So for an energy level, the value of J is 6. What will be the degeneracy and energy value? So we know degeneracy is defined as mj 2j plus 1. And what is the value of rotational energy level? Which rotational energy level we are talking about? J equal to 6. So we can put here 2 into 6 plus 1 is equal to 13. We have two options that has 13 mj value. That is 13-fold degeneracy. Okay. 13-fold degeneracy. And the second thing asking energy value. So the energy is given by, I am writing in terms of wave number. For any jth rotational energy level is given by B j to j prime j plus 1 centimeter inverse. Okay, so this is in centimeter inverse unit. So this is 10 centimeter inverse, and we have 6. So we will have 1042 centimeter inverse. So that is 420 centimeter inverse. So this is the correct choice. Okay. Now coming to the summary of lecture 18. Okay. So in actual case, we are considering a molecule. Let's say we have a molecule A. We have a diatomic molecule that contains atoms A and atom B. While rotation, we consider this bond as rigid. But the question is, why this bond has to be rigid? Okay. So in actual scenario, this bond is not rigid. Okay. So to explain that, first let's try to see the rotational data of HF molecule. Okay. So we are seeing here, this is like a frequency for different rotational lines, and this is the gap. Like we will have, this is the 2b, this is nothing but 2b. And so first, so we can see this b, rotational constant. So we can see here, as we are increasing, like as the jth rotational energy level increases, this value of rotational constant, that is b, is decreasing. See, it's decreasing. So the question comes, why is it so? Okay. So if you see this R is nothing but bond length between HF molecule. So this is this. Okay. So we are seeing here that as J increases, the bond length for HF increases. So what does it mean? It means while rotating, this bond will not be rigid, and as we are increasing the J value, that is as we are increasing the energy, the rotation becomes faster and faster. Let's say this is your center of mass axis and this is our molecule. Okay, and it's rotating along this axis. This is omega angular velocity. So this angular velocity will increase with so this angular velocity will increases with j, and higher the value of this angular velocity, we will have higher centrifugal distortion. So what is this centrifugal distortion? So while rotating, some force will act on outside direction. Okay. Force will act on outside direction. And because of, let's say we have two atoms, A and B, and when this AB molecule rotates, some force outside is acting on the molecule. Because of that, this bond length will not be same. Okay. So the bond length will not be fixed. The bond length will keep changing. So as we increase the J, this frequency will increase and the bond length will increase. Okay. And as bond length increase, meaning higher the centrifugal force. Okay. So let's try to look from this figure on the right side. So we have two atoms M1 and M2. And this point is center of mass. So we can simply consider like this. Okay. One molecule with reduced mass mu. Okay. And after rotation, it's the final distance is r1. Initially distance was r0, and after rotation it's r. Like this bond length or the distance from center of mass has increased. Okay. So some force is acting on this direction, but we will have some force acting on this direction. That we will call restoring force, Fr. And this is centrifugal force. Set equilibrium, both will be equal, Cr, and from here we can calculate R, this Rc. So this R is actual distance from the center of mass while rotating. So we can see here that this R is dependent on this angular frequency, angular velocity. Angular velocity. So higher the value of this omega, so I'll write here higher omega, this denominator mu omega square will be smaller, and this R will be higher. Okay. So we saw here that this omega depends on J, that is with increasing the value of J, this omega increases. As a result, this R increases. Okay. So this R increases. And this frequency so we call this non-rigid rotor. Non-rigid rotor. We will see in the incoming slides that how this centrifugal distortion, or because of this centrifugal force, the energy level of the non-rigid rotor is different from the rigid rotor. So we will solve this in the incoming slides. Okay. and we will this one also we'll solve in the incoming slide, this frequency of any rotational level after centrifugal distortion. So if you see in the next slide, we solve for rotational energy or energy for any rotational level using classical mechanics and quantum mechanical restrictions for this angular momentum, and we found that this Ej is given by this equation, and we can convert this Ej into the wave number. We will get something like this. Okay, but we saw in the previous slide, here we have minus sign, but after derivation we got something plus sign. Okay, so we consider the distortion R is very small, like R minus R naught is very small number, small number. And to simplify this, we will replace this R with R naught. Okay, then this minus sign will come. Further, we know that this I is this tensor or this moment of inertia is given by mu R square or mu R naught square. So we can write here this I, we can replace with this mu R, it becomes this. So this whole term, we call this D, and this D is centrifugal constant. Centrifugal constant. Okay. So we saw that the bond length or any molecule is not rigid while recording rotational spectra. Okay, and we also saw that how can we calculate the energy of any rotational energy level or frequency of any rotational energy level. Okay, and then we can calculate the transition, like energy required for the transition from J to J plus 1. Okay, so we can express in terms of wave number, that is delta nu J bar, and that is nothing but, so we can express this equation as B J J plus 1, and this term we can call D J J plus 1 का whole square. So this is wave number of energy of any rotational energy level. So if you want to calculate the energy required for any transition, then we have to take the difference, and the difference is this equation. And for HF molecule, something we got like this. So this is nothing but your 2B if you compare from this equation, and this is nothing but your D. So if we know D and if we know B, we can calculate the vibrational frequency of the bond because of rotation. So because of rotation, this bond is not rigid now. It's kind of a spring, so it's a vibrate. So what is the vibrational frequency? So that vibrational frequency we can calculate from this. Okay. So let's try to look upon some problems. So the first question is how the rotational energy level and energy of rotational lines change for non-rigid molecule. Draw a rotational spectrum. Okay. So first we will write energy. This E is nothing but B J J plus 1. For now, let's ignore this centrifugal distortion term. Okay, we will try to explain this with the help of this beta. And this B is rotational constant. rotational constant. Change the ink color, and if you write the B, it is h 8 pi square I c. So you can see here this B is inversely proportional to I. What does it mean? If the moment of inertia of a molecule, or if the tensor of a molecule increases, this rotational constant decreases. As a result, the energy of any rotational energy level decreases. Okay, and we further see this I is nothing but mu r square. So if the molecule is rigid or non-rigid, this will be constant because the mass is not changing. Okay, so this is constant. So what is changing here? This r, this bond length is changing. Bond length is changing, meaning this r is directly proportional to r square. So we can write here B is inversely proportional to 1 by r square. And we also saw that this r is directly proportional to j. From the table and from our explanation, we saw that this r, the bond length, increases as the rotational quantum number increases. Okay, so what we can say then, let's say we will draw one rotational spectrum. Let's go to next slide. So I will write here rigid one side, okay, and this side non-rigid. So we have some rotational energy levels E. So draw something. So I will say this 0, 1, 2, 3, 3. So we have transition from here, here, considering delta J plus minus 1. This is only the allowed transition. Okay. So you'll get something like 3 rotational lines. 1, 2, 3. This gap is 2b. Okay. These are called rotational lines. Okay. Now, when the molecule becomes non-rigid, in that case, what we are seeing, this R value increases with increasing J. And when the R increases, we saw this B decreases. When the B decreases, this energy decreases. So energy of every rotational energy level will decrease. So let's say the energy of this level will decrease like this. It will decrease like this, and it will decrease like this. So we can see here, as the value of J increases, this drop in energy or decrease in energy is higher. Okay, so I will say this 0, 0, 1, 2, 3. And if you draw the rotational spectrum, so this, and here this. So this gap will be smaller than this gap. Okay, because this energy difference. Energy difference of this is smaller than this. Correct. So because of the centrifugal distortion, the energy difference between two energy levels will keep on decreasing. Okay, and this decrease will increase with increase in J quantum number. As a result, what will happen? The separation between rotational energy levels, rotational lines, is no longer 2b. Okay, So based on this discussion, let's try to solve some problems. So the first problem is we have three consecutive lines in the rotational spectrum. So let's say we have three consecutive line, 1, 2, and this third. This is at 84.544. This is at 101.355, 118.112 centimeter inverse. All the numbers are in centimeter inverse. Now the question is asking this line we are getting because of which J prime to J transition, J double prime to J prime transition. So we have to calculate this J. Once we calculate this J, then we have to calculate the vibrational frequency of the molecule. As we discussed, if you can know the B and D, then we can calculate the vibrational frequency of the molecule. Okay. So the frequency is given by some frequency of some jth level is given by 2b j plus 1 d. Forgot the question. I'll see again. 2b 4d. Okay. Excuse me. So 2b and this 4d j plus 1 whole cube. This is the equation for wave number for transition between corresponding two energy levels. Okay. So I will say this equation 1, and for three lines it's given. So we can write here 84.544 centimeter inverse is equal to 2b j into j plus 1 4d j plus 1 cube. I will say this equation 2. Similarly, we can write here 101. It's not only j plus 1. So sorry, it's only j plus 1. 101.355 centimeter inverse equal to 2b. Here we'll have one higher, j plus 1. So I am directly writing j plus 2. So j equal to, in this case we will have j equal to j plus 1 or higher level, because these lines are consecutive lines. So let's say this is j, this will be j plus 1 and this will be j plus 2. Okay, these are consecutive lines. So you can write here minus 4d j plus 2 cube. This is, I will call equation 3. And the fourth one, 118.112 2 centimeter inverse is nothing but 2b. I will write directly here j plus 3 minus 4d j plus 3 cube. I will say this equation 4. Okay. So from the given equation we wrote three equations: equation 2, equation 3, equation 4. Okay. So let's try to work on equation 2. From equation 2. From equation 2. Okay. So we know that this B is much greater than D. This is in, let's say, 1th order, then this is in 10 to the power minus 3 order centimeter inverse. See, like orders of magnitude lower, than B. D is orders of magnitude lower than B. So for determination of J, for sake of simplicity or sake of determination of J, we are ignoring this term, this second term, because this D term is very small. So we can write here 84,544 is equal to 2B J plus 1. Okay. And we can write here no, sorry, excuse me. I did some mistake here, so I'll cross this term. So we'll take the difference. So we will try to calculate this difference. So we'll take from equation 3 minus 2. Okay. So what we are getting, 101 left hand side minus 84.544 on the right hand side. We will have 2b, so I will keep b terms together. I will take 2b common and then I will write here minus j minus 1. And the second term is like, I will take 4d common and I will write j plus 2 cube j plus 1 cube. Okay. So as I said in the previous slide also, since b is much greater than d, so this second term I am taking approximately 0. Then we will have something like 16.811 centimeter inverse is equal to 2b. This j will be cancelled out. Okay. So from here b is equal to something we can divide here, 16.811 divided by 2. So we got something 8.4055 centimeter inverse. Okay. So one part is done. One part of the equation is done. Now we will try to calculate the value of j from equation 2. So equation 2 is some 84.44 centimeter inverse is equal to 2b. We got 16.811 centimeter inverse and then j plus 1 after ignoring the d term, because as I already explained, the value of d is very smaller compared to b, so second term we are ignoring in equation 2. Okay. So by solving this, we got j is equal to 4.03. It can't be in fraction, okay, it will be in whole number, integer. So we are taking that nearest integer, so j will be 4. Okay. So we estimated the value or we calculated the value of j. Then if you draw this rotational line, we had 3 rotational lines, 1, 2, 3. So this will be 4, 5, 6. So the transition is taking from 4 to 5, 5 to 6. And the third one is 6 to 7. So 4 to 5, but these are the rotational lines, so we cannot draw this. This is not transition. This does not represent transition. But this line, this rotational line is coming because of transition from 4 to 5. This is coming from 5 to 6, and this is coming from 6 to 7. Correct. So we calculated the transition, like between which rotation level the transition is happening. Okay. Now coming to the next part of this question, we have to calculate D. Okay. Here's D. Inside here one more slide. Now we found the J. J is 4. So from equation 2 and 3. Okay. Or you can use equation 3 and 4 also. I am just using equation 2 and 3. So that was 84.544 centimeter inverse. 2b, and j I am keeping 4, so it will be 4 plus 1 minus 4d and 4 plus 1 cube. Okay, so we can write this 84.544 centimeter inverse 2b into 5 minus 4d into 125. So I will say this equation 5. Similarly, from equation 3 we can get something like 355 centimeter inverse is equal to 2b into 6 minus 4d into 216. So by solving these two equations, we know the value of b. We know the value of b. We got something, see, b 8.400, 8.4. So we know this 8.4055 centimeter inverse. So from any of these two equations, you can substitute this b and you can calculate this d. On doing so, I am getting value of d this approximation is not that correct, because this b will change because the bond length is changing, but this rotational level will not change. So this expression, this assumption is correct. Assumption, but this b we cannot calculate like this. Okay, because this b is changing in case of non-rigid rotor, so we cannot consider. Sorry for this. But this rotational energy level, in rotational level or J quantum number will not change. So in that calculation you can ignore D. Ignoring D. but you cannot ignore here. Can't ignore D. Okay. So this is kind of two linear equation, xy variable. Sorry for this. This is kind of two linear equation. So when solving this two equation, we got B 8.473 centimeter inverse and D 3.7 10 to the power minus 4. So we can see from this calculation also, like around 3 order or around 4 order of magnitude are smaller than B. D is around 4 order of magnitude are smaller than B. So that's why in calculation of J, we ignored D. Or physically we can think like that, because of this non-rigidity, this jth quantum number will not change. The energy for the jth quantum number may change, but this quantum number itself will not change. So that's why while determination of J, we ignored D, we take D as a 0. And from calculation also we see that this D is very small number. Now we got D, B and J, like this transition, possible transitions. Now we have to calculate the frequency of the vibration. So let's say if the molecule is rotating, because of rotating the bond is also vibrating. So what is the frequency of that bond? So we can calculate that using this equation. D is nothing but your 4b cube nu square. So we have to calculate this nu. So that will be your 4b cube D under root. Then you will substitute all the value. For B is 8.473 centimeter inverse cube, 3.7 10 to the power minus 4 centimeter inverse. Okay, we will solve this, we will get something 2564.4 centimeter inverse. So we can estimate the frequency of the vibration of a bond because of rotation in any energy level J. Okay, clear, right? Okay, then we're moving ahead. The second question comes a similar question. See, we have rotational constant, that is B, is given by 10.593 centimeter inverse, and D is 5.3 10 to the power minus 4 centimeter inverse. Now the question is asking to calculate nu bar, so we can calculate 2b cube, or it's 4b, I think. It's 4b cube by D. So B is given, D is given, so it can be calculated easily, right? Now second question is force constant. So force constant is, it's a 4 pi square c square mu r square. So from this expression, it's not r, it's nu square. Using this expression you can calculate this force constant. This is force constant. So this nu we can get from here, and this we can plug in here. And reduced mass can be calculated. Mass of hydrogen multiplied by mass of chlorine, mass of hydrogen plus mass of chlorine. So I'm not doing detailed calculation. You can calculate this number. The value is given here. Okay. So we can calculate reduced mass, and we can calculate this frequency of or vibrational frequency because of rotation. We can calculate this number from this equation, and we can plug in. We can get force constant in some Newton per centimeter or Newton per meter. Okay. So this problem I'm leaving on you guys. Try to plug in the value and try to get the force constant. Okay. Because similar problem I solved before, like calculation of nu bar. So still this is I'm not solving here, and we know how to calculate the reduced mass. So it's pretty straightforward. You can solve it. Okay. So till now we saw like we considered diatomic molecule, only molecule having two atoms. Okay, and we saw all the possibilities, like in case of rigid data, in case of non-rigid data, in case of in presence of electric field, in absence of electric field, all the problems we saw there, effect of isotopes, and what are the information we can get, we saw there. Now coming to polyatomic molecule, because in the real system there are many polyatomic molecules instead of diatomic. Okay, so how can we treat those systems then? So polyatomic molecule is kind of, we can consider extended rotating object, like it's not symmetric, it's kind of extended object. See, in that extended object we saw in the lecture 2 that this omega, that is angular velocity, and L, that is angular momentum, need not point in the same direction. So in that case we can define angular momentum L as I omega. So here the L and this omega are vector quantity, and this tensor is not vector quantity. So this is like your matrix, and this is a 3 by 3 matrix, and this is also matrix. So for particular choice of axis, let's say we are considering x-axis, y-axis, z-axis, not in the middle of that. So for particular choice of axis, this off diagonal term will be 0. These are off diagonal term, and this term is diagonal term, diagonal element. Okay, so off diagonal elements become 0 after consideration of particular choice of axis. So from here we also saw that the principal axis of inertia are A, B and C, and corresponding principal moment of inertia is IA, IB, IC. And we also saw in the lecture note, or if someone has not seen, then please refer to lecture 19. There you will find that this IA will be lesser than equal to IB, which is lesser than equal to IC. So we have three moment of inertia based on principal moment of inertia. So based on this I's, we can classify molecule as symmetric top or symmetric rotor. We can say rotor. Similarly, sorry, a spherical top or a spherical rotor, symmetric top or symmetric rotor, asymmetric top or asymmetric. So we will try to understand what is a spherical top, what is symmetric top, what is asymmetric top, based on these three tensors or three moment of inertia. Excuse me. So based on these I's, we will try to classify the molecule into three categories. First is a spherical top, or we can say a spherical rotor. Second is symmetric top or symmetric rotor, and third one is asymmetric top or asymmetric rotor. Okay. So before this slide, we saw like we treated only diatomic molecule, and we did not worry about this thing, no classification. Okay. But when we consider the polyatomic molecule, this classification is must. Okay. So we'll see the first one, the spherical top or a spherical rotor. We will see the conditions. So if you see this, a spherical top, in case of a spherical top, we will have IA equal to IB equal to IC. That is, principal moment of inertia will be same. Okay. So examples of these categories is tetrahedral molecule, that is CH4 or CCl4, SF6 or SCl6 does not exist, SF6, and this is C60. This is icosahedral, not octahedral, icosahedral. So in this case, in this category, in a spherical top category, we will have IA equal to IB equal to IC. Okay. And the second one is symmetric top or symmetric rotor. So in this category, we will have two class. First is prolate and the second one is oblate. Okay. So if you see the conditions based on this principal moment of inertia, for prolate, here it will be, for prolate, this IA will be smaller than IB, which will be equal to IC. So for any molecule, this is the condition we saw there. IA will be smaller than equal to IB, which will be smaller than equal to IC. And considering this, the condition for prolate, it will be IA less than equal to IB, which will be equal to IC. Examples are CH3Cl, CH3Cn. Okay. And if we see the oblate, this is the condition, IA equal to IB, which will be lesser than IC. So this we can call rod-like or linear rod-like, and this is disc-like. What is the meaning of this rod-like then? So if you draw the structure of CH3Cn, so we see most of the masses are concentrated around this circle. This kind of rod-like shape, correct? Or we can draw this one also, CCl. We know that the atomic mass of chlorine and carbon are much higher than hydrogens. Okay. So most of the mass of the molecule will be concentrated here. Okay. So that's why we call rod-like. Okay. And if you see the CHCl3, we can draw this tetrahedral structure. And this atomic mass of chlorine is much higher than this hydrogen. Okay. So because of this, the mass of this whole molecule mostly will be centered towards the chlorine, towards this circle. You can see here. It's kind of disc, correct? So that's why we call disc-like. Now, till before this two slide, we have studied diatomic molecule, only diatomic molecule, rigid rotor, non-rigid rotor. So based on this discussion, can we say that this diatomic molecule comes under a spherical top or symmetric top? So let's consider one molecule HF. Okay. So I'll write here HF. Sorry. So I will write here HF here. Let me change the color of the pencil so that you can see clearly. So this is one axis, I will say X, and this is your center of mass. I will say this is CM, center of mass. So this is another axis. Okay, I will say this Z, oh, Z, and the perpendicular to the plane, perpendicular to XZ, we will have Y. See, the molecule lies on x-axis. So the distance between the molecule and the center of mass, between the bond and the center of mass, meaning the R will be 0. And the moment of inertia is defined as I equal to mu R square. So along the x-axis, I will be 0. Okay. And on the y or z axis, we will have similar moment of inertia, because the R will be same and the moment of it, this reduced mass will not change in any direction. So the moment of inertia or tensor I will be same in along z axis or y axis. So we can say this IA. Why we can say this IA? Because from this condition we see that this IA is smallest. So that's why we can say this IA. Okay. And the other two value along z axis or y axis, it's equal. So we can say this B greater than IA, because this IA equal to 0 and this is non-zero. So of course this IB and IC is not equal to 0. So this all the linear molecules that we studied before, doesn't matter is rigid or non-rigid, comes under the category of prolet and is a class of symmetric top. Okay. Now coming to the third class, which is asymmetric top or asymmetric rotor. So in that case we can see the condition that IA not equal to IB, which is not equal to IC. One disclaimer, IA need not be equal to IXX. Usually in crystallography, A axis we call X axis usually, and B axis we call Y axis, and C axis we call Z axis. But here this tensor IA need not be equal to IX. We have to follow the condition. Which condition? IA will be lesser than equal to IB, which will be lesser than equal to IC. Okay. So keep in mind, this one also need not be equal to IYY. This one also need not be equal to. It can be, but need not be, not necessarily. IZ. Keep in mind. Okay. So the example of this case is chloroethene. So along the all direction, you will have different tensor or different moment of inertia because of, see here we have hydrogen, here we have chlorine. So along B axis, along C axis, along A axis, we will have different moment of inertia. And this comes under the category of asymmetric rotors. Similarly, you can consider water molecule. This is water molecule. So I will say this y-axis, I will say this z-axis, and the perpendicular of this xy, perpendicular of this yz will be x-axis. Okay. And somewhere here we will have some center of mass. Okay. So along every direction, along x, y, z direction, we will have different moment of inertia or tensor. We will solve one problem also, like how can we decide or how can we calculate the moment of inertia in all directions. So we have some problems in the incoming slides. Okay. So based on this I value, we classified in three categories, broadly in three categories: spherical, symmetric, asymmetric. In symmetric, we have two categories: prolate, oblate. Okay. So based on this summary, based on this discussion, let's try to solve few problems. I will come to this lecture again. So first we will try to solve the problems. So I'll take H2O molecule, and we know the bond length. This R is bond length between bond length of OH bond. OH bond. And this theta is the angle between this angle. I'm not writing there because I have to draw some schematic there. This angle is 104, approximately 5 degree. Okay. So how can we calculate the moment of inertia along x-axis, y-axis and z-axis? So to calculate that, first we have to assign the center of mass of the molecule. So it's somewhere here. Okay. This is center of mass and this is the center of axis. Okay. So I will draw a line here in middle. This is to use geometry, and this is our y-axis, and this one I am considering as z-axis. Okay. So this total angle is theta. This total angle is theta. I am saying this theta. So this will be your theta by 2 half. Correct. So to calculate moment of inertia along y direction, we need this distance. Correct. The oxygen atom lies on y-axis, and for polyatomic molecule, we know that this moment of inertia is nothing but summation I, mu I r I square, or in terms of atomic, we can write this one I m I r I square. See, this oxygen atom comes on y-axis. So in this expression y we need to consider only mass of hydrogen, because the distance between y-axis and the oxygen atom is 0. Sorry, we are calculating based on this axis. Sorry, so we cannot ignore oxygen here. We need to consider oxygen also. So MO, this I will say RO square, and there are two hydrogens. So we need to multiply 2 MH RH square. Okay. This R0 I defined this one, or simply this line, this distance. So how can we calculate that? Any idea? So this total angle will be around, this total angle is 180, and we know this angle we know. Okay, and this will be equal to this, so I will say this phi, and this is also phi. So how can we calculate this? Or we can write this distance, so we can calculate this is sine phi is your this length, so I will write here this RH and this bond distance OHR. and we can substitute this value here. Similarly, you can calculate along y-axis or z-axis. For like clarification, I kept here. These things are discussed in the lecture note, in the lecture 20. So you must go there. And based on this analogy, we will try to solve some problems. Based on what we discussed, we will try to solve the problem. And if you have any doubt in the lecture note, then you can ask anytime. Okay. So, first question is, for the carbon dioxide molecule, which of the following relation between three components of moment of inertia axis is correct? So we will look into carbon dioxide. Okay, this is CO2. So if you see the structure of CO2, it's linear. So this is linear triatomic molecule. Okay. And this one I will call x-axis, and this one I will call z-axis, and the perpendicular to x and y I will call y. So the moment of inertia I along x-axis will be 0. Why? Because r 0, and the I is defined as mu r square. In other two direction, y or z, it will be I will be equal. So in that I y y will be equal to I z z. Why? The molecular symmetry. Okay. If the mass distribution along both axes is different, then in that case reduced mass, or sorry, moment of inertia will be different. So based on our analogy means this assumption, IA less than equal to IB, which is less than equal to IC. We can see the moment of inertia along x-axis, that is IA. IA will be 0, which will be lesser than IB, which will be equal to IC. So which option is correct? This second. Okay, so coming to the next question. So the following relation holds true for which of the following. This one is already solved there. It's S of 6. 1 and this tetrahedral molecule CCl4. Okay. Coming to next question. For symmetric top, there are two subcategories. Which are they? So we saw the prolate and oblate. So for prolate, so for symmetric top, we have two categories. One is prolate, other one is oblate, that is rod like and disc like, and we saw the condition IA can see here. So these are the conditions. IA less than equal to IB equal to ICN here. IA equal to IB less than equal to IC. These are two conditions. Correct. So based on this, which one is correct option? The first one. Okay. Now coming to next question. From the following molecule, there is one prolate, one oblate. Choose the correct combination. So CH3CN, CO2, C6H6, SF6. Okay. So we already saw there the CH3CN. The structure is like this. Hydrogen, in this hydrogen comes under category of prolate. We already discussed this, how it comes under prolate category. We already discussed it. Okay. And the second molecule CO2 we saw is also under this category. It's also come under prolate category. We saw that is linear structure, and we saw this condition IB equal to IC, and we saw this I becomes 0. Okay. And the benzene, nitrogen, and the third one is SF6. So SF6 does come under which category? A spherical top, octahedral. So it come under spherical top. Okay. So the question asking one prolate, one oblate. So it must be some these two combination or these two combination. So combination could be CH3CN, benzene, and or CO2, benzene. Okay. So this is the correct answer. Second one. Okay. Now choose the correct combination. So we saw prolate is kind of disc-like structure. Sorry, rod-like structure. And oblate is disc-like structure. Okay. But if you see the this BF3, so the structure is linear. The structure is linear. So the center of mass is somewhere here. So mass is concentrated like this kind of disc. Okay. And we saw there that CH3CN, it's like some kind of CN, hydrogen. Mass is mostly concentrated at here. It's like a rod like. So disc like is oblate and the rod like is prolate. Okay. So which will be correct option? This one. Okay. Now coming to the last slide or last questions of today's discussion. So we have this trigonal planar molecule. Okay. So we have to show this one I x x equal to I y y, which is equal to 3m by 2, and I z z equal to 3m. Okay. So how can we solve it? So this is your center of mass. This is your center of mass, and all the bond length are unit length, means 1. Okay. Bond length is 1. So we need this distance. Correct. This distance. So this angle is 120. So this will be your 30. This is 30 because total is 180. So this will be your 30 degrees. So we need to find this distance. So sine 30 degree is equal to, I'll say this r by this bond length is 1. Okay. So r is some kind of sine 30 degrees kind of 1 by 2. So r will be your 1 by 2, 1 by root 2. Now let's calculate IXX. So here IXX will be I'll say 1 2 3 4 now. Okay. So it will be m1 r1 square m2 r2 square plus m3 r3 square, and masses are in m unit, and the value of r, this r doesn't matter the direction, it will be same. So 1 by root 2 square, similarly m 1 by root 2 square, m 1 by root 2 square, so it will be 3m by 2. By 2. Similarly, we can calculate IYY also. It will come around 3m by 2. And IZZ is nothing but summation of IXX plus IYY. So it will be 3m by 2 plus 3m by 2 equal to 3m. So what we got here, this we will got IC. Okay. And this you can call IB or IA. This you can call IB or A, doesn't matter. So what we got, IA equal to IB, which is lesser than IC. So this is which condition? Oblate or prolate? This is oblate. So if you draw the analogy here, one mass is here, one mass is here, one mass is here. This kind of configuration. So if you don't know this configuration, by using this kind of calculation, by calculating moment of inertia, we can predict. So we classified the molecules in three categories, but it does not matter that those molecules will show rotational spectrum. For rotational spectrum, the molecule must have permanent dipole moment. Okay. So from this all discussion, I'm not discussing the origin of the selection rule. I already discussed in the last session. Like what is the origin for the selection rule? Like why we have this has to be the molecule has to have permanent dipole moment. Why only delta J equal to plus minus is allowed? All that this thing I discussed in last session also. So please refer there. And here we are ending rotational spectroscopy. If you have any question, then you can write in comment box. Thank you.